Hello, my name is Will Simonson, and today I'll be going over the Lab 5 following Slinky lab. So the objectives in this lab are to analyze the motion of a Slinky using tracker, and then code the motion and capture the models, and also analyze how the Slinky moves. The main concepts of this lab are Newton's second law, which is the final velocity equals the initial velocity plus the net force divided by mass times the change in time. And also the net force equals the force of gravity plus the force of drag plus the Slinky force of tension. Also, the gravitational force is equal to negative mg. The drag force is the absolute value of velocity squared times the v hat, and Slinky has a tension force. So the system is the Slinky, and the surroundings are the Earth, which counts as the force of gravity and the drag force. So here's the tracker video. You can see here that the value as predicted, the Slinky stays in the same spot at the bottom for the first 6 or so seconds, and then the bottom drops. And you can see that this drop right here is somewhat linear. It's moving at a constant speed. So for the code, the initial position and the mass of the ball is used along with the change in time and the force in g and the negative g hat vector and the drag force proportionality to calculate the forces that are acting upon the Slinky. You can see here that the time goes till the final time in the tracker video, and the forces are calculated by multiplying some of the values said earlier together. The velocity is found using Newton's second law and the velocity update formula, and then that is then plugged into the position update formula using delta AT and looping it over and over. So the results of this lab, you can see here that this is the graphed portion of the coded model, and you can see here that 1 through a little over 6 seconds, the bottom of the Slinky, which is the point that we are looking at during this experiment, is staying in the same place, which was predicted before the experiment, and then moves in a somewhat linear fashion in position. So this is the coded model, and there is also a tracker model, and these are compared. And as you can see here, the glow script has a more linear, they both lose y value at a similar point, but the glow script predicts that the ball will fall faster, or the Slinky will fall faster, while the tracker predicts that the Slinky will fall slower, and also have, because of human error in the tracker, not complete constant velocity. Some sources of error for this experiment is the drag force could have some error in the model because it's not always precise with the mass or the surface area of the Slinky, which is taken into account in real calculations when finding the drag force. And also the Slinky mass that was used is not actually the exact Slinky mass with precision that would give results of an experiment of high accuracy. In conclusion, you can see that the Slinky mass at the top of the Slinky fell first, and then the bottom of the Slinky fell. Thank you.